Okay, now to the second part of this lecture. It's the shorter part. It's getting sunny here Tuesday morning. Move into the shade a little bit. Something is wrong. Yes, I forgot to share slides. It's good I remembered. It has happened to me earlier to forget that, then I have to do everything over. Now I am sharing screen. So now I think it's working. Okay, so this part is a little bit outside maybe the main course, but it has to do with the modeling stuff about the vaccines. That is that the vaccine I mentioned earlier that suppose it reduces the risk of getting infected by some fraction. That is not well defined. It could either be that it could either be well, it could be in two different ways, or probably most often in somewhere in between. And one is called the leaky vaccine, and the other one is called an all or nothing vaccine. So a leaky vaccine is a vaccine where each person that gets vaccinated has a reduced risk. So if the risk of transmission at each contact is reduced from P, so P is some probability. Each time you have a contact, you have a probability P to get infected. But if you are if you have a vaccine, this thing is reduced to P times theta. So if theta is 0, it means that you have no risk of getting infected. If theta is 0.5, it means you have 50% reduced effect of getting infected. So each contact, everyone who gets the vaccine has a reduced risk of getting infected each time they are contacted. Another possibility is, I guess this is probably the way most people think of vaccines, that it reduces your risk. You still have a small chance, but each time you get contact, you have the same risk. Another possibility would be that you can say that the vaccine works in a fraction 1 minus theta and has no effect at all with probability theta. So if you vaccinate 1,000 individuals, a fraction of them, the vaccine has no effect, and the other fraction, they are completely immune. So each vaccinee has probability 1 minus theta of becoming fully immune, and the other probability theta, with the remaining probability theta, the vaccine has no effect whatsoever. Both of these vaccines are said to have vaccine efficacy 1 minus theta. Here, everyone has reduces the risk of infection by to theta, and here instead the community fraction 1 minus theta become completely immune, and the remaining have no effect. So both of these have the same vaccine efficacy with regards to susceptibility, and it equals 1 minus theta. And the critical vaccination coverage is 1 over 1 minus theta multiplied 1 minus 1 over R naught. Well, then the question is, are these two vaccines equally good? I mean, perhaps you don't know what the vaccine, how the vaccine works, but perhaps you know the efficacy. Which one would you prefer? But also in terms of estimation, if you don't know, maybe you want to be conservative, and then which of these two would give a more conservative estimate? It is not too hard to show. I think you could do that. Most students could do that, and I encourage you to try to do that. That the probability to get infected if you are contacted K times, so if you have K infectious contacts on you, the probability to get infected will depend on if you have a leaky vaccine or if you have an all or nothing vaccine. And it is possible to show that the probability to get infected is always larger if the vaccine is leaky as compared to if it is an all or nothing vaccine. So assuming that they have the same vaccine efficacy theta, or same vaccine efficacy 1 minus theta, then the probability to get infected after K contacts is bigger if the vaccine is leaky. That means that the final number infected will be at least as large, for the leaky will be at least as large as the all or nothing. So this is called stochastic domination. So there would be more infected stochastically if the vaccine is leaky as compared to all or nothing. But the other way, if there is no vaccine at all, there will of course be even more people getting infected. But the basic thing is to show that this thing is equal for the two vaccine if K is equal to 1, but this expression is larger for a leaky vaccine when K is larger than 1. This means that if a community is vaccinated, but not enough people are vaccinated for herd immunity to appear, then the all or nothing vaccine reduces transmission the most. It is, in a sense, the better one. So the all or nothing, if you have two vaccines, one is with the same efficacy, one is an all or none, and the other one is a leaky, the all or none is better. However, a more reasonable description is the following. So if you have a vaccine and you don't know if it is a leaky or if it's an all or none, then the leaky one is the worst case scenario. So if you want to be conservative, you should assume that it is a leaky one. So your estimate of vaccine efficacy is larger if you assume the leaky. So if you estimated the vaccine efficacy assuming that it was an all or nothing, when it is in fact it is a leaky one, you will have an underestimate of the vaccine efficacy. So it's hard to keep in mind which direction things go, but if you think a little bit more about it, this will be the case. So if you don't know what effect the vaccine has, you should make sure that you choose the conservative one so that you don't get an underestimate. It is much better. Yes, it is better to underestimate the efficacy than to overestimate it. Now a few words about the reproduction number, which we will discuss at the live session. So the basic reproduction number, one way of thinking of this, if you remember, the definition is how many on average people infect in the beginning of an epidemic outbreak. But you can think of this as a factor of three, as a product of three factors, where the first one is the probability of transmission given a contact, multiplied by the rate at which people have contacts, multiplied by the average length of the infectious period. What is a contact here is, of course, sort of vaguely defined for many diseases. For instance, for COVID-19 and influenza, sometimes there is a definition that you are within 1 meter's distance and you talk to each other for at least 2 minutes. That is one definition, but of course it's rather arbitrary. There is not, so there is no distinction. This was a contact. This so also if you talk, of course, if you talk shorter than 2 minutes, there is still a risk of transmission. So it's not clear what is the definition. Whereas for other diseases, for instance, sexually transmitted infection, then the contact is more clear cut. It's a sexual intercourse. But anyway, you can think of R0 as a product of these factors. And then when you think about preventive measures, you can aim at reducing the first one, the second one, or the third one, or of course all three of them. Anyway, if you reduce it by a factor C or C of t, if it's time varying, then the new effective reproduction number is the basic reproduction number multiplied by 1 minus C. This we discussed earlier, and also in Mikael's lecture it was about this. And we know that there will be no outbreak if R0 is small, RE is smaller than 1, which is equivalent to that you must have reduced the R0, the fraction of contacts by this much. And you could aim at reducing P, K, and L, and that is something we will discuss in the live session on Thursday. I think this is a little bit repetition from before, but if the epidemic has got going, then after a while some people get infected. So after a while a positive fraction have become infected, so then the effective or the current or the daily reproduction number can be noted RE of t. I think Michael called it simply R of t. That's just as good, I think. So it is a factor which tells how much transmission has been reduced, multiplied by what fraction are still susceptible, multiplied by R0. And I want to emphasize that this relies on a homogeneously mixing community. If it was not homogeneously mixing, then this R0 should also vary with time, because it should reflect how many contacts people that get infected at time t, how many infectious contacts they have if everyone was susceptible and there was no reduction. Because typically in the beginning of the outbreak, the more outgoing people get infected. So later on in the epidemic, this quantity actually also reduces with time. And of course, the common goal is to keep this value below 1, because whenever it is below 1, the epidemic will decline, whereas if it is above 1, it will rise. So that's equivalent to having the fraction of the reduction should be at least 1 minus 1 upon R0 times the fraction currently infected. I noticed that here I have fraction, where I think Michael has numbers, but no, maybe not in this expression, but I think in Michael's lecture, beta was the contact rate between one infected person and one susceptible person, whereas I had beta as the contact rate between one infectious individual and all others. So we have slightly different notation, so this must be kept in mind. So one thing that we will discuss, and I will create this breakout room, is for a few different diseases, I want you to think about what are some preventive measures that can be inserted to reduce spreading and that are used, and if the effect of them is that they reduce P, they reduce K, or they reduce L, or if they reduce several of them. So that is something we will discuss. You can think of COVID-19, but you can also think of HIV or other sexually transmitted infections, or measles, or influenza, or some other disease. Okay, that was the end of lecture 7, and we will meet on Thursday. And then there is a break on Thursday. We will hand out assignment 1, or handout. It will be available on the course webpage. And then there is a break until August 4th, but you have a deadline for home assignment 1, which is August 1, if I remember correctly, but you should look on the course webpage when it is, when you find it, what is the exact deadline. And of course, you have the possibility to ask some general question on the discussion forum. All right, with that, I end this recording and see you on Thursday.